All right, today we're going to dive deep into the fundamental nature of matter itself. I'm talking about the very stuff that makes up, well, you, me, this entire planet, and everything else in the universe. And our whole journey starts with one pretty amazing question.
Think about this for a second. Could a single puff of air, something you do thousands of times a day without even noticing, actually hold the secret to diagnosing something as serious as lung cancer? It sounds like science fiction, right? But scientists are working on this as we speak, figuring out how to spot tiny things they call biomarker molecules in the air we exhale.
So how on earth is that even possible? Well, to get it, we need to rewind the clock. Way, way back. Because the key isn't hidden in some futuristic, high-tech lab. It's actually in a simple, brilliant idea about the building blocks of everything, a puzzle that took people thousands of years to finally piece together.
Okay, so our story begins in ancient Greece. This is where the first great debate about what everything is made of really kicked off.
Now look at this timeline. It shows something kind of crazy, actually. A massive gap. Back in the 5th century BC, you have the first ever proposal of atoms. But then, for more than 2,000 years, another idea completely took over, and progress on this huge question just stopped. It basically hit a wall until the early 1800s.
So here are the two big ideas that were battling it out. On one side, you had guys like Democritus saying, hey, if you keep cutting stuff up, you'll eventually hit a tiny particle you can't cut anymore. He called it atomos, which means uncuttable. But then you had Aristotle, a pretty big deal at the time, who said, nope, everything is made of fire, earth, air, and water, and you can just keep dividing it up smaller and smaller forever. But, there was a huge problem with all of this. For all their brilliant thinking, these were just, well, ideas. They were philosophical arguments, not scientific theories. Nobody was actually in a lab running experiments to see who was right. And because of that, for 2,000 years, our understanding of matter just stood still. That is, until an English school teacher came along and just changed everything. This is where the real revolution in chemistry begins, with a man named John Dalton.
So in 1807, John Dalton comes onto the scene, and he's different. He's not just sitting around thinking. He's looking at the data from actual experiments. And he noticed all this weird behavior with gases and how chemicals combined, and he realized it all makes perfect sense if you just assume that matter is made of atoms.
He boiled it all down to 5 simple rules. 1. Everything's made of tiny particles called atoms. Easy enough. 2. A pure element like gold is made of only one kind of atom. 3. Atoms of different elements are different from each other. 4. Compounds, like water, are just different atoms stuck together in simple whole number ratios. And 5, and this is the big one, in a chemical reaction, atoms just get rearranged. They don't get created or destroyed.
And let me tell you, this wasn't just some neat idea. It was like a master key. It suddenly started unlocking all these chemical mysteries that had scientists scratching their heads for ages.
Take something called the law of definite proportions. It sounds fancy, but it's basically like a recipe for a cake. It just means that if you want to make a specific cake, you always need the same ratio of flour to sugar to eggs. A pure compound is the same. It always has the exact same recipe of elements by mass, no matter where it comes from.
And check this out. This table shows it perfectly. We've got 3 different samples of isooctane, which is a part of gasoline. Look, the samples are all different sizes, but when you do the math and find the mass ratio of carbon to hydrogen, what do you get? The exact same number. Every single time, 5.33 to 1. Dalton's theory explained why. Every molecule of isooctane is built with the exact same number of atoms.
Okay, that's pretty cool, but his theory could also solve an even weirder puzzle, the law of multiple proportions. This is where it gets really interesting. What happens when the same 2 ingredients can combine to make completely different things? How does that even work?
For example, you can take copper and chlorine, and you can make this green crystal. But you can also take copper and chlorine and make this totally different brown crystal. They look different, they act different, but they're made of the exact same 2 things. So what gives?
Well, scientists went to the lab. They took exactly 1 gram of copper and measured how much chlorine it took to make each of these compounds. For the green one, it was 0.558 grams of chlorine. For the brown one, 1.116 grams. Okay, so far, those just look like numbers, right? Kind of random.
But here's where the magic happens. They weren't random at all. Because when they divided the bigger number by the smaller one, they didn't get some messy long decimal. They got 2. Exactly 2. A perfect, clean 2-to-1 ratio. Wow.
And that's the whole secret. This wasn't magic. It was just atoms. It meant that the brown compound has exactly twice as much chlorine for every copper atom as the green one. So maybe the green crystal is 1 copper stuck to 1 chlorine, but the brown one is 1 copper stuck to 2 chlorines. Simple whole number ratios, exactly like Dalton's theory predicted.
And just like that, we've come full circle. This really simple but incredibly powerful idea that atoms combine in specific ways is the foundation for some of the most cutting-edge medical science happening today. Because remember that breath test for cancer? Those biomarker molecules they're looking for, they're just unique little packages of atoms, specific compounds, arranged in a very precise way that your body might only produce when a certain disease is present. It all comes down to counting the right atoms in the right combination.
I mean, it's hard to overstate this. Dalton's idea isn't just a footnote in a textbook, it's the bedrock of modern science. It lets us understand disease, design new life-saving medicines, create the advanced materials in our phones and computers, and even figure out the secrets of the entire universe.
So think about that. A humble school teacher gave us the key to understanding the building blocks of literally everything. It really makes you wonder, doesn't it? With all the incredible tools and knowledge we have today, what fundamental secrets are we on the verge of unlocking next?